Okay, let's look at problem 732 from the 12th edition. We have this beam that's shown, and we need to draw the shear and bending moment diagrams and determine the maximum values of the bending or value of the bending moment. Okay, so before we can do anything, we need to figure out what's going on at this spot here. So this type of joint is going to have a force here. We'll call it Cy, Cx, and I can draw the moment in that direction because it's easier to see. And the moment at C. Okay, so what we're going to do, the first thing, so going back to chapter 5 type stuff, we're going to replace this distributed load. I'll do this in a different color. We're going to replace this whole distributed load, right, with a single load at a single point. And that single load is the area under that curve, which happens to be WL. Well, it's the length times the width, right? So W times L over 2, which is obviously WL over 2. And where is it applied? It's applied exactly in the middle of that, which is going to be at L over 4 in this direction. Okay, so when we do our, come back here, sum my forces in X equals 0 is going to tell me that Cx equals 0. Lovely. Sum my forces in Y is equal to 0 is going to tell me that Cy is equal to WL over 2. And then lastly, sum of my moments, we'll call it about C equals 0. Okay, so then we have WL over 2 times the distance from there, which is going to be L over 2 plus, so what is 3/4 L is going to equal to, that's going to go that, so that's going to equal to the moment at C. So the moment at C is equal to 3WL squared over 8. Okay, so now we have the unknowns. So now we've done the stuff that has nothing to do with chapter 7. So now let's start our chapter 7 stuff. And by that, I mean we're going to draw the shear and bending moment diagrams. Okay, so let's, I'm always torn, and we'll do it here. So we have this beam here, so we have the distributed loads halfway across the beam, and then we have some loads going on here. That was an awful arrow. Try that, I'll draw it this way. Moment there. Okay, so let's look at the shear forces first. Okay, and then, so I'm drawing this like here. I kind of like to do it like this so I can kind of put events so that they all make sense together at the same time. Okay, and here is the bending moment. Okay, so first off, let's look at just this real point here. The shear is going to start at 0 because there's no shear there, and it's going to slowly increase. And how much is it going to increase? Well, we know that it's going the W, the distributed load, is the slope, so it's going to come down like this at a constant rate until it gets to this value right here is minus WL over 2, right? Because it's going to, for everything X that goes in that direction, it increases by W and then ends up going all the way over to L over 2 before it gets there. So W times X, or WL over 2. And then it stays constant across there because there are no loads there. And then remember this right here is WL over 2. So then it's going to go pop back to there. So that, I mean, we're going to color this in. Kind of. I kind of missed, but don't tell anyone. There we go. There is our distributed load. Sorry, not our distributed load. That is our shear moment curve. Now, the shear, shear moment. That's the shear. Now the moment curve, let's look at the moment curve. Okay, so what do we know about the moment curve? Well, we know that it is the area under the curve is the change here, and we also know that the moment is the integral of the shear. And so what does that mean? Well, this short version is since we know this is a straight line coming across here, this is going to go in a second order curve to there. And since this is constant across here, therefore this goes straight from that point. So it's not the prettiest curve, but you can kind of see what I'm doing. Okay, and that becomes our moment curve. So it's actually not too bad, right? So let's think of what this means. So what is this value right here? Well, it's the area, since it's the change is the area under this curve, and since it starts at 0, well, and it comes back to here. It starts at 0, and the area, we'll call this A1, is equal to WL over 2 times L over 2 times 1/2 base times height, right? So that is 1/8 WL squared. And so this one right here is therefore minus 1/8 WL squared. Okay, that's fair enough. Now, from here to here is the area under this curve, right? So we'll call this A2, and that's just minus WL over 2. That's this value times the length, which is L over 2. So that is minus WL squared over 4. So from here to here is WL squared over 4. And since they're starting at 1/8, we're going to go down to 3/8 WL squared. And then if we're looking for the maximum bending moment, which is what is being, so that is drawing the shear and bending moment diagram. Boom. Now we're looking for the maximum absolute value of the bending moment. Well, it's clearly right here. So it's a negative value on it, but we're looking for the absolute value. And so for part B, the max is 3/8 WL squared. And boom, you're done. There you go.